Good afternoon. Hello, and welcome to today's webinar entitled Best Practices for Integrated Machine Safety. Today's presentation will be given by Kevin Monin. Kevin is a consulting applications engineer with Siemens Industry and focuses on both North American technology promotion for motion control safety and CNC machine tool applications. He is a 30-year veteran of the machine tool industry with specialized interests in domestic and international standards. Since 2002, Kevin has been actively involved in the introduction and acceptance of functional safety technology in the U.S. and Canada, working with both large and small machine tool OEMs and end users. We've got a very informative session planned for you today, so without further ado, welcome Kevin.
Thank you, John, and welcome everyone. Before I begin, I need to include a general disclaimer regarding this particular presentation. While I will be covering a lot of material aimed at broadening your knowledge on the topic, this information is for educational purposes only. Before acting on any of the information that I present or talk about, please check with a recognized expert on the subject matter to ensure that the application of any information shared in this presentation is appropriate. Thank you, and let's move into the presentation. We have approximately an hour. And in that hour, I would like to give you an introduction to motion control safety terminologies, a rapid-fire review of new and revised machine safety standards. We'll talk very briefly over the risk assessment process, which is becoming very important to standards both domestically and internationally. We will take a deeper dive into motion safety functions themselves. A conceptual view is what we will do due to the time limitation, but the objective will be to give you, if you're unaware of motion safety terminology, particularly what the new standards and regulations are bringing to the table, particularly what that terminology is and some of the basic concepts behind it. We will also talk briefly about OEM and end-user acceptance testing of safety-equipped machinery, programmable safety in this case, and I'll provide you with several sources of additional information where you can go to find deeper information to continue your knowledge. What does safety mean in the context of this discussion? For our purposes, we're talking about functional safety, the operation of a machine, the prevention of unexpected operations or unexpected failures. So safety in general is electrical shock, heat and fire, hazardous radiation, and we will talk about hazards due to functional faults, and I would extend that statement to include hazards due to machine design, control system design, operational considerations of many types, maintenance, machine building, rebuild, repair, operation, and maintenance. So that's the area that we will focus on today. Why do we talk functional safety? Principally, we talk functional safety to make the workplace safer. With the introduction of such technologies as linear motor machines, PLCs, programmable CNCs, we are seeing for many years machines that move faster, machines that are more complex, and machines that require the similar operation, maintenance, and setup requirements. So for our purposes today, and to provide a concise definition of machinery, I'm going to fall back to one of the standards, particularly I'm going to paraphrase RIA 1506, the robotic standard. Machinery for our context means an assembly of linked parts, at least one of which moves with actuators, control, and power circuits. We also can consider machinery an assembly of machines. And why is that important? Because a failure or operational fault endangers health, endangers the human, and also, of course, endangers the machine. What are the basics behind the safety systems for machinery? The basics are we detect, we evaluate, and we respond. And any of the complex safety systems from Siemens, the programmable safety systems, the integrated systems as we call them, to safety relays, to even a push button and a solenoid, all fall into the category of detect, evaluate, and respond. So we will break down the systems into those three categories today. Detection can be as simple as an emergency stop push button, can be as complex as a programmable light sensor. Evaluation can be as simple as a safety relay or as complex as a programmable safety system. The response or the responding actuator can be a contactor, a hydraulic cylinder, or possibly a safety drive system. So that's a key takeaway message from today is the principle of safety systems is detect, evaluate, and respond. So let's look at a simple safety circuit so we can all move to the same page in our thoughts. This is the classic safety relay from Siemens. As a sensor, we have an emergency stop, dual channel switch, and it has a direct opening contact. Basically, we call that a force-guided contact. There's no springs, there's no compliant mechanism inside that switch. And the reason that is done is so if one of the two contacts in that switch happens to weld shut, we don't want to be able to press that actuator and not realize that both internal contacts switched states. So that is an important feature and has been for many years in the safety technology is what is called direct opening or force-guided contact. So now we have our sensor. We've connected our sensor to a safety relay. Its job is to detect the open or close state of that emergency stop switch and to set its outputs accordingly. Its diagnostic purpose is to test and sense the wires going through the switch to look for opens, shorts, etc. The respond, or the actuators in this case, are two contactors near the bottom of the page. Those are wired in series to the little motor, which is a three-phase motor. So now we have, in essence, a complete circuit. We have detect, we have evaluate with the safety relay, we have respond with the actuators. We've actually taken this diagram a step further, and up in the top right-hand corner, we have a blue push button. So we have the capability to reset or reactivate the circuit after the emergency stop is pressed. And the reason we want that capability is so the motor does not automatically restart when we release the emergency stop push button. So that's a very basic, simplistic example of a safety system, but very appropriate. It's not unreasonable, even to meet today's international standards and regulations, that we could use this circuit that would be very reasonable if it meets the need, it solves the risk, and it works appropriately for our implementation. There's nothing in the standards that I can read that tells me basically what type of safety system I have to use. And we'll talk about this a little bit briefly in a few minutes. The concept is we use the appropriate technology to reduce the risk to a tolerable level. So we'll take that slide a step further and look at what we would call a traditional safety design. In this case, we have the detection, which in this case is showing an emergency stop, a light curtain, a laser scanner, etc. We have the evaluating or the evaluation piece, which is a safety relay, again in this case. And then we have the responding mechanism. Similar situation, we have two three-phase contacts, in this case paired with a drive system, a non-safety rated drive system, with the automation, the non-safety rated standard automation controlling the drive. This is traditional system. It gives us the capability to respond to the emergency stop in this case and open the contactors in the drive circuit. This works very well in some cases. Several difficulties come into play, particularly electronic drive systems do not like contactors in their circuits. And also, we can look deeper into the machine design that this might be applied to and realize that the safest way to stop when the emergency stop is pressed may not be opening the contactors in the drive system. It is typical that we need to use the conventional control system to stop, in this case, a servo motor, bring it to a stop before we open the contacts to the drive system. So even though this circuit works very well in some cases, it becomes limited very quickly when we look at the safety of the entire system. So let's take a step further and look at a integrated safety design. This design can be anything from a safety PLC, a safety CNC, or any number of higher level safety control systems. So we have the detection, again, emergency stop and other sensors. We have the evaluation, which in this case has changed from a safety relay to a safety control system, what the standards would call a safety rated control system. This unit from Siemens, in this case a Sinumerik PLC, has the capability to do both standard logic for the process or machine control, in addition to safety control, all on the same platform. So in this case, the safety PLC becomes the evaluation step for our safety system. The response mechanism, or in this case the actuator or servo, is now a safety-rated drive system. You'll notice that there are no contactors in series with the drive system. Recent changes in the U.S. standards, NFPA 79 in particular, in the last several years, have allowed the use of safety-rated drive systems in this manner to perform this function. No longer do we need a contactor in the three-phase supply system to reach the desired level of functional safety. You will see this acceptable both domestically in the U.S. and Canada, acceptable in the European Union, the European Machinery Directive, of course, and acceptable internationally. So this is what I would consider best practice. We have the opportunity for the standard control system to bring the drive to a stop under control, along with the safety system to monitor that result. What do we gain from this? We typically increase the level of safety, functional safety. We many times increase the flexibility of this implementation so that if we need to refit or modify the implementation as we retool, it typically is much simpler to reprogram a programmable safety controller than it is to rewire and redesign a safety relay system. Now let's take a look at some motion safety terminology. The definitions, and these are not all inclusive, but the definitions I show here are according to IEC 61800-5-2. This standard, international standard, is used to define functional safety for variable speed drives. And this standard 61800-5-2 defines functions to stop a drive, functions to monitor motion, safety relevant motion, and functions to look at position, to do things such as zone demarcation, safe software cams. So let's take a brief moment and look at these a little bit closer. We need to drop back just a moment and think about stop categories. And in this case, I'm going to refer to NFPA 79, the machine tool standard here in the USA. And the machine tool standard defined several types of stops. A stop category 0, a stop category 1, and a stop category 2 are the ones that I want to talk about briefly. Stop category 2, notice I did not say a safety stop, but a stop category 2 is immediate removal of power from an actuator. The classic would be press the emergency stop and you removed hydraulic pressure from a cylinder, or you freewheeled a servo motor or a spindle and allowed it to drift to a stop. So immediate removal of power. Stop category 1, the definition is we bring the, in this case, the servo axis or the actuator to a stop, and then after that stop or a predetermined time period, we transition to a stop 0. So stop category 1 brings the machine to a stop and then transitions to a stop category 0. A stop 2, by our standard definition, is we bring the axes or the machine to a stop, and at that point we retain control, full torque, full servo, full hydraulic pressure, etc., so the machine is still under control. Now let's correlate those with the safety stops, and luckily they match up very well. Safe torque off, STO, is the safety equivalent of our traditional stop category 0, immediate removal of power. Safe stop 1 is the safe equivalent of a stop category 1. The axis, or machine in this case, comes to a stop, and then we transition to STO, or safe torque off. Safe stop 2 is the equivalent to a stop category 2, which is bring the axis or machine to a stop and then maintain position. So for the purposes of our discussion, these 3 categories of stops, safe torque off, safe stop 1, safe stop 2, match up very nicely with our traditional stop categories. The additional one here is the safe brake control. The brake is controlled safety relevant, which we will talk about in just a bit of detail in a few moments, but the case here is where there's a dual channel control reliable circuit that controls the brake, in this case possibly a vertical axis on a milling machine, and the brake is on the ball screw or the servo motor and is applied to stop gravity from pulling the axis down and the axis falling. If we look at the motion monitoring functions very quickly, safe direction is a safety function to guarantee only direction of the motor or the actuator in one direction. Safe limited speed, a very highly used function, is the ability to safely guarantee that the axis or actuator in question will not move faster than a pre-configured speed. We would use this on a machine tool as an example. When the operator door is open, we could use this function to limit the speed of the axis to 2 meters per minute as an example, and guarantee that under no failure circumstance that's covered by the safety function that that axis would exceed that speed. That allows us to meet our risk assessment, which we'll talk about briefly, where the risk assessment says when the operator door is unlocked or opened, that the speed of the axes must be limited to a certain speed. So this is the capability we can use there. For position functions, we have safe limited positions, which is a safety implementation of physical safety switches on the machine. We can now do that with the safety system itself without the need for additional hardware. Safe software CAMs is just that. It's a safe programmable replacement for physical CAM switches, typically redundant CAM switches on a machine. And safe operating stop, which is a methodology that a safety system uses to monitor and hold a axis or an actuator in position. And we would use that function when we have example, an operator door, the door is open, and I need to tram a spindle, or I need to work in that environment, and I want to guarantee there can be no movement of the machine. So, a brief introduction to the motion safety terminologies. Let's take a quick look at some of the new and revised machinery safety standards. Depending where you are in the world, and if you're a machine tool builder or an end user, if you export machines or import machines, you may run into a number of standards and regulations and jurisdictions that are not harmonized, or in other words, the regulations, the requirements, the common practices don't match up. In North America, we're typically looking at Underwriters Laboratory, the Canadian Standards Association, ANSI. In Europe, the European norms. In Japan, the JIS, the Japan Industrial Standards. And then as an umbrella, and in some places harmonized with local domestic standards, would be the international standards from IEC, the International Electric Technical Commission, or the ISO organizations. And those standards are typically what we see as being state-of-the-art and best practice. Kind of an eye chart here, but I want to give you just an overview of some of the functional safety standards that you need to be at least aware of. ISO 13849, the standard that is replacing EN 954-1, which we'll talk about in this talk also. OSHA in the United States, the Code of Federal Regulations. 1910 is important from a machinery safeguarding, risk reduction, lockout, tagout perspective. NFPA 79 I've already mentioned as a machine tool standard, the ANSI B11. And then if you work in robotics, you should be familiar with ANSI RAA 1506, the robotic standard. That standard is in draft revision, and it looks to be, again, that ANSI RAA 1506 will be setting the lead for the robotics industry. And it's also of note that many other industries, particularly the machine tool industry that I are involved in, will reference RAA 1506 for such topics as risk assessment and best practice. So let's look just a bit deeper into some domestic USA standards. NFPA 79 has just been revised and was published just recently. It's the 2012 edition. No major changes from the previous version, 2007, in regards to functional safety. The big changes, from my perspective, revolve around wireless or cableless pendants and continue to harmonize or attempt to harmonize with European and international standards. The ANSI B11 series, of course, for safeguarding are very important, and in particular, I suggest you become familiar with ANSI B11 TR3 for the topics of risk assessment and risk reduction. Also, there's at least 5 standards that refer to risk assessment. RAA 1506, as we show, NFPA 79, etc. And several of those, including ANSI B11 TR3, ANSI Z244.1, and the RAA 1506, provide some methods for risk assessment. So it's very worthwhile to take a look at those standards to get an understanding of the risk assessment process if you don't already have that methodology and capability if you're a machine tool builder or if you're an end user. And let's talk a minute about OSHA. OSHA's impact on functional safety. Typically, it's somewhat difficult to tie the United States, in particular, standards and regulations together with enforcement, together with OSHA, together with ANSI, etc. Functionally, there is a connection between OSHA and the machine tool standard NFPA 79, and the connection comes through the ANSI standards. What is important here is that the standards and regulations in the U.S. are typically voluntary. They are consensus standards developed by industry and are voluntary from compliance. That is effectively different than the European community, where standards or regulations, or in this case compliance with the European Machinery Directive, are mandated by law. In the United States, that situation doesn't exist. In the United States, the end user is responsible for workplace safety. That makes the end user more interested, in my opinion, in the risk assessment, the safety functions on the machine, and that allows the machine tool builder also to utilize any number of standards and regs voluntarily to comply. A best practice scenario is where the machine tool builder and the end user utilize state-of-the-art best practice standards such as NFPA 79, Z244, and even the international standards to follow as guidelines for their implementation. A brief look at the European standards. You must note that EN 954-1 has been removed. Starting several years ago, ISO 13849-1 2006 was implemented with the goal of replacing EN 954-1. That process started in 2007. That process of replacing EN 954-1 completed at the end of 2011. Why is that important here in the USA? EN 954-1 effectively was the mother standard of NFPA 79, and EN 954-1 is one of the standards that introduced safety categories, from what we are familiar with Category 2, 3, 4, etc. Since that standard has been removed, those safety categories are still supported by ISO 13849-1, but they've been supplemented with quantitative analysis of the safety systems, where the safety categories were qualitative in nature. How safe do we believe the circuit is? How safe has it been in practice? The new standards are moving towards a quantitative analysis where we can mathematically define and derive the safety of the system. So the key here is if you're using EN 954-1, that standard is no longer viable and has been replaced with 13849. Beyond that, standards of great interest to the machine tool industry would be EN 62061, which covers electrical and electronic safety technology, and EN 61800-5-2, which I mentioned earlier, which is a product-specific standard, and it deals very well with variable speed electric drives and integrated safety systems. So a pictorial time chart of where the standards, both from Europe and internationally, have come from and transitioned to. We see that at the beginning of 2010, the 2006 version of the European Machinery Directive went into place. Also at that time, EN 954-1 was actually extended an additional 2 years, and that was due to quite a bit of difficulty, in my opinion, in applying the new standard 13849 successfully and universally. So we've reached 2012, which indicates EN 954-1 is no longer valid, replaced by 13849. And we also see that EN 62061 has been available since 2006 and continues as we speak. Principally, we use 62061 when we have electrical subsystems, and 13849 is very good at more than just electrical control systems and drive systems. It also supports hydraulics, pneumatic devices, and those other pieces of machines that we typically encounter that historically EN 954-1 did not embrace or deal with very well at all. So now let's take a look at a risk assessment, just a very basic risk assessment procedure. The reason I include this piece today is that in the United States and Canada, internationally, particularly outside of Europe, we may not have a long history of doing risk assessments, and if we do risk assessments, we may not publicly make that information available to, in this case, a machine tool builder selling a machine to a customer, or an end user asking for the machine tool builder's risk assessment. So how does this procedure work? This specific flow chart is out of one of the standards, and they're all basically the same, and they follow the concept of reducing a risk to a tolerable level. In practice, you define the hazards on the machine: trip and fall, a vertical axis falling. I need to insert a tool into the spindle, and if the spindle rotated unexpectedly, there's a hazard. Any of those hazards that can be identified, and then we define the tasks, what tasks have to be done on the machine. And this ranges from when the machine is being built to the machine being shipped, torn down, put back together, maintenance, setup, operation, the entire life cycle of that machine, what hazards can be expected. So we define the limits, we identify the hazards, we assess the risk, and we make a determination if that risk is reasonable, also could be tolerable, also called a residual risk. Now, that is an objective term, reasonable or tolerable residual risk, and that varies by industry. But generally, is the risk tolerable? If it is tolerable, then we do not have to mitigate that hazard. If the risk is not tolerable, we have to find some risk reduction method. The best practice is to design the risk out of the machine. If that's not possible, then we start looking for protective measures like a safety control system that we can put in place that can reduce that risk to a tolerable level. So the takeaway message here is that more standards and regulations are embracing the risk assessment procedure. The risk assessment procedure is similar across industries. It does vary some between industry to industry. The important piece is that a risk assessment is performed, that all the identified risks can be reduced to a tolerable or residual level. In general, how do we define the risk? Three pieces are conceptually used, and we won't go into much detail here. But the risk assessment or the risk is defined as the severity of the injury. Is it severe? Is it a slight injury? You see the word irreversible used here sometimes to define severity. What is the frequency, or how often is the human, in this first case the operator or setup person, exposed to that risk? Is it frequent? Is it seldom? And then how can we eliminate or avoid the risk? If it's a slow-moving machine element, then it's probably very likely I can avoid that risk. If it's unexpected, or if it's such a nature that I can't avoid it, then that would make the possibility of eliminating very unlikely. So three pieces are used to define the severity, the frequency, and the possibility for eliminating are used to define the risk. And this is generally consistent across all the risk assessment methods. So let's take a brief look at some of the motion safety technologies in a little bit more detail. The change, as we saw earlier, is going from conventional or traditional relays and componentry to an integrated safety system, in this case, a safety CNC and a safety drive. That technology has been moving this direction since 1994. In the case of Siemens, when Siemens introduced the first safety CNC, and many other technologies have moved forward also. And within the past few years, we've seen standards such as NFPA 79 start to embrace the technology as early as 2007, and the international standards also in that same time frame. So let's take a look at Siemens drive safety in this particular case. Just a pictorial example of how a servo system may be designed to provide safety functions. Key takeaway message here is dual channel, control reliable, fail-safe. In this case, we have in the center of the screen channel 1 and channel 2. Two separate circuits, two separate processing systems, two separate channels controlling a motor module, using the redundancy and possibly the diversity capability to provide protection from failure. In the motor module itself, in this case, two opto-isolators, each controlled by one of those channels. In the DC supply or the output section to a servo motor, we have 6 IGBTs or power transistors. In the case of a three-phase servo motor, we have to commutate that servo motor with a proper electrical pattern to get the motor to rotate. If either of the channels do not fire their opto-isolator, that in essence will not fire the IGBT or power transistors, and the servo motor cannot move. So now we have the capability to functionally control this motor. Electrically, we're still connected to the power source, but functionally, the dual channel fail-safe redundant control system can stop the motor from commutating. taking that a step further, let's refer to the safe torque off, one of the safety functions defined by the standards. Safe torque off, if you remember, is freewheel, immediate removal of power. In this case, when the safe torque off function is active, the drive system does not commutate the motor, it does not fire its power transistors, and the motor coasts or freewheels to a stop. The key point here is we are functionally safe, we are not necessarily electrical safe. Remember that the motor is physically connected to the drive system, and the drive system is still energized, even though the fail-safe system does not allow the motor to commutate. So the safe torque off function in no way, shape, or form removes the function for lockout, tagout for electrical safety. The motion safety functions provide motion safety, not electrical safety. So the safe torque off function is implemented to allow immediate removal of power. Safe stop 1, if we remember, is bring the, in this case, the servo motor to a stop, and after a predetermined time interval or reaching a stop condition, transition to a freewheel or safe torque off condition. Same situation, the control system drives a set point of 0 or brings the servo motor or axis to a stop. When that stop is achieved, it transitions to safe torque off or freewheel, synonymous with the stop category 1, in this case, the safe stop category 1 or safe stop 1. Note again, the DC link can remain energized, the bus system. There are no contactors in the circuit, so this is purely an electronic implementation. Safe stop 2 is exactly as we described earlier. Bring the axis or servo motor, in this case, to a stop, but retain control for full torque, full standstill. Now we monitor the machine for movement, and if the redundant control reliable safety system sees any movement, then it will react accordingly. So we would use this function when we want to bring the machine to a stop, be able to open that operator door of that imaginary machine that I talked about earlier, and now using the safety function, I can leave the axis powered, I can leave the servo system active. If I have a vertical axis, I can leave the vertical axis under servo control, use the brake as a backup if I need it, the physical brake, and use the safety system to provide the functionality. Now I don't have to necessarily rely on a vertical axis brake or mechanical clamps on the axes. These are safety-rated functions that can provide this capability. Safe operating stop. We talked about safe operating stop briefly. It's a methodology to monitor a machine that's in a standstill condition. So the safe operating stop would be asserted while I had this operator door open on this machine that I'm imagining, and the safe operating stop safety function, its role is to monitor the machine for movement, and if it detects any movement onto the machine that's outside its configured tolerance band, then the safe operating stop function is going to respond and respond in a safe manner, whatever that fail to save condition has been configured to do. The importance of this function might be that machine with the operator door open, I have safe operating stop active on my vertical axis, I'm holding my brake in reserve, and the safety system discovered that the axis is dropping. My fail to safe implementation in my application software is most likely going to apply the mechanical braking system as the redundant or backup brake system, and in this case, being able to avert a physical axis from dropping by using the brake as the reserve. So safe operating stop is just that. It's a methodology for controlling a machine at a standstill condition. Safe limited speed, my absolute second favorite function over safe operating stop, is the ability of the safety system to guarantee that the axes or the servo motor or whatever our safety mechanism is does not move faster than a pre-configured speed. If we dig deep enough, we're going to find a European standard, possibly a DIN standard out of Germany, that many years ago published a 2 meters per minute reference to axial movement with an operator door open. Now I'm paraphrasing, but that was the intent. Using that 2 meters per minute, I now can use my risk assessment to indicate how fast that axis is safe, and I may decide on my machine that maybe 1 meter per minute is my safe speed to meet my risk assessment, and I can use the safety system to implement that safe limited speed at 1 meter per minute. So no matter what happens as a failure or a machine operator turning the feed rate override to 150%, whatever the case may be, in my imaginary machine with the operator door open, when I'm exposed to the risk, my safe limited speed is set at 1 meter per minute, and if that axis exceeds that speed for any reason, the safety system will bring that axis to a stop. So I've met the intent of my risk assessment to only allow the axis to move at that pre-configured maximum speed. Safe brake control is just that. It's a redundant braking capability, and in Siemens' case, we have the opportunity to control this brake directly from the servo drive, and by doing that, we do not need additional contactors, relays, involvement from a PLC, etc. So now the brake can be controlled directly from the servo, which tends to reduce application errors and also gives us a fail-safe, redundant, safety-rated brake control system. Safe communications. Over the last couple of years, Profibus, Profinet with Profisafe, the communications protocol Profisafe, has given us the capability for safety controllers, in this case a Sinumerik CNC from Siemens, communicating with either an additional CNC or a safety PLC from Siemens or others, the capability to safely communicate between control systems. Where this becomes very powerful is in a production line system where I have a gantry loader servicing multiple Agile machines. Historically, that safety-related communication and status was communicated between safe relays using bundles of wire. Today, and best practice would be implement a Profisafe communication link between those safety controllers and send that communications across that communications link. Gives us added flexibility, reduces cost, and increases our reliability from a safety perspective, from a failure perspective. So let's take a brief look and a very quick look at some end-user acceptance testing. Typically, the standards and regulations indicate that the safety system must be implemented per manufacturer's instruction, and also says that the system must be tested and documented. Many end users, many machine tool builders also have this requirement. In this case, I'm showing a Sinumerik Safety CNC acceptance test, and Siemens has a semi-automated wizard that helps with this process, but the concept is similar across all the safety systems where we must test and document the implementation. Historically, if I have a safety relay and an emergency stop and a contactor, my safety system checkout was a checklist and a meter in my back pocket, and I would press the e-stop, I would listen for the relay, I would check voltages, make sure the contactor changed state, and that was my test. Functionally, we do the same thing with the safety system, but because the safety system is more complex and is typically integrated, we have to have some more complex measures and maybe some higher level functionality from the control system to do our functional tests. In Siemens' case, the Sinumerik NC engineering tool for the safety CNC is what I'm showing here. This is actually a very excellent tool. It allows scripting of the test so that the test can be canned, so they can be executed multiple times by, let's say, someone that's not the safety system designer, that doesn't have the expertise in applications. This test can be canned and scripted so that this test can be run, as an example, by a contractor brought in to help with acceptance testing. Because in this case, once the test scripting is developed, execution of the test is just that. It's execution following a prescribed set of instructions. So a very good tool from Siemens. Other manufacturers have tools that are somewhat similar, but I would consider this one of the best and definitely a state-of-the-art tool for acceptance testing, in this case for safety CNCs. As part of any acceptance procedure is the documentation, and I have this slide here just to indicate the type of charts and graphs and documentation you'll see. In this case, the classic 3 charts that indicate the response to a failure condition. In this particular case, it could have been that 1 meter per minute velocity that I had configured maximum with the door open. During our testing, we will violate that 1 meter per minute and record, graph, chart, document the response of the safety system. So this is a very quick example of such an implementation. How did you do this if you supply machines into Europe with the CE mark or you're a European-based manufacturer? Very similar. Your machine must comply with the European Machinery Directive, of course. And the particular takeaway point here is the last bullet for machines with special hazards, as in a manually loaded punch press. You cannot self-certify. The testing certification must be done by an external testing body that is resident or legally involved in the European Union. So takeaway message here, in not all cases can you do your own acceptance test and certifications if you are or are exporting into Europe. So in just a few minutes we have here, let's take a look at some additional sources of information that you might be able to utilize. In this case from Siemens, the safety evaluation tool, which we'll talk about just briefly in a moment, is an engineering tool that allows us to do that quantifying analysis of the safety system to create those numbers to meet the standards, particularly for the European Machinery Directive. If you use EN ISO 13849 or 62061 as an example, you need to do the math to determine the reliability of the safety system and its components. Functional examples from Siemens, there's a wealth of information on the internet with pre-configured, documented functional examples for you to use as a basis. SI-Train, the Siemens training system, has formal classes available. Of course, we have what we call the Siemens hotline or support. The website link is shown here. Definitely use that for questions or support requests, for general information or for specifics for that matter. And generally from industry in general, all manufacturers, include Siemens, have a wealth of information on their websites. So I strongly suggest that you take advantage of these resources to come to grips with the standards and regulations that are changing very quickly within the last few years. Functional examples. I show a screenshot here of just the beginning of the list from Siemens of a wealth of functional examples that are documented and downloadable for your use. The safety evaluation tool. It's an internet-based online tool from Siemens. It is TÜV or TÜV certified for use within the European Union and also internationally. You use this tool, as I said, to quantify or mathematically calculate your safety system probability of dangerous failure, which is a requirement if you're complying with a few of the standards I just mentioned, 13849, 62061, etc. There is a Sistema tool also available. It's a non-Siemens tool. It is a very good industry-based tool, also free based on internet availability, which also gives you the capability to do these mathematical functions that are required to meet today's standards and regulations, particularly the standards 13849, 62061. And for European standards, a few links here. You can use these links. You can search, of course, on the internet, 62061, 13849. I strongly suggest you investigate. And if you want to understand the European Machinery Directive and where the European and international standards are heading, go to newapproach.org. There are some very good discussions on the intent and the concepts of the standards, regs, and machinery directive. That being said, I'd like to open it up for questions and answers, realizing that this was a very fast, rapid-fire overview. John, if you have some questions, we could work through those now.
Absolutely. A couple questions have come in. The first question is, would it be possible to get some information on safety standards for robotic applications?
Absolutely. NCRIA 1506 is one. And if you look at the Robotics Industries Association, RIA, there is a wealth of information available. Also, your control supplier, whoever your robotics control supplier or a robotics control manufacturer, also would have a wealth of information. Feel free to email me. My email address was shown earlier, and I'm sure will be published as the presentation is made available. I can help you individually with that information.
Okay. The second question that came in during the presentation, we manufacture a drilling machine that uses a window-based PC as its controller. How do I integrate the motion safety functions that I need with a desktop PC?
Interesting question, very appropriate. We all know that a Windows, not to bash Windows, but a Windows PC has a tendency for such things as a blue screen of death, or it is a non-safety rated controller in this particular question. To meet the European Machinery Directive, as an example, to meet NFPA 79 or other standards, regulations that would apply, manufacturers such as Siemens have drive-based capabilities where the controller, in this case the Windows PC, does not need to be a fail-safe controller, but the built-in safety functions in the drive. I'll refer back to safe torque off, the freewheeling stop category 0 safety function, the safe stop 1, bring the axes to a stop or bring the actuator to a stop, and then transition to the safe torque off or freewheel. Those type of functions, up to and including safe limited speed, are available in the drive systems themselves, sometimes with some slight additions to the hardware and a bit of configuration. That system can be made fail-safe to meet the needs of your risk assessment and does not rely on the host controller, in this case a Windows PC, for its safety functions.
Okay. Another question in the few minutes that we have left. I'm a Siemens solution partner, and I retrofit drives and control systems onto existing machines. Do I have to conform to the latest functional safety requirements when retrofitting a machine?
Interesting question. We have to start to define what retrofit or possibly rebuild or repurpose means. Typically, if you are doing nothing more than rebuilding, and rebuilding being brought back to the exact configuration it was when it's new, you typically do not need to comply with most newer functionality requirements. But if you are retrofitting, we're putting a new control system on a machine. We may be putting a new control system and new servo drives on a machine. In that case, you are fundamentally changing the design of the machine, and for all legal intents and purposes, anything that you touch, anything that is related to what work you are doing, up to and including a machine control panel out on the machine for a tool changer, needs to be looked at very closely, and I would strongly suggest, and best practice would be, to bring it up to common day standards. But if you're just rebuilding a component in the machine, I'm replacing a drive with the same model, same function, that usually doesn't require bringing it up to standards. But if you're doing any improvement work, then yes. Particularly if you're in Canada and in Ontario, the Ontario Ministry of Labor with the Pre-Start Health and Safety Review has some very stringent requirements. But in general, it's good practice to bring those pieces that you're working with and those pieces that foreseeably you were affecting up to current standards.
Okay. Let's see if we can squeeze a couple more in here. The next one, I am a domestic machine builder and I export to Europe. My existing safety system utilizes safety relays only. Is this satisfactory to meet the European Machinery Directive?
The answer is going to be it's based on your risk assessment. There's nothing that I am aware of in the Machinery Directive, and if you would use EN ISO 13849-1 to show compliance with the Machinery Directive as an example, there's nothing that I am aware of that says you must use a certain type of safety system. So if my risk assessment supported the use of that safety relay technology, very possibly I have a simple machine with a conveyor that has limited risk and my risk assessment is done properly, accurately, and with all due diligence, and it is deemed that the implementation I'm using is satisfactory, then by all means, that should be a very viable solution. It is not the case that more complex is always better. We try to use the appropriate technology to provide the best solution, which is not necessarily the most complex solution.
Okay. Next question. EN 954-1 is withdrawn, replaced by EN ISO 13849-1. As a machine tool builder in the U.S., how am I affected?
Interesting question. EN 954-1 brought the concept of safety categories B, 1, 2, 3, 4 to the table that NFPA 79 also utilizes. The very effect of EN 954-1 being withdrawn does not make your current solution impractical or invalid. It does concern you that you are not using any specific features out of EN 954-1, excuse me. So effectively, in the U.S. today, there is no significant impact. Of course, each case has to be reviewed individually, but the takeaway message is the U.S. has not embraced the enforcement or the adoption of EN ISO 13849-1, and NFPA 79 was closely harmonized with EN 954-1. So I would suggest that you look closely at those standards that do apply, NFPA 79 in particular, I would suggest, and if you comply with applicable standards domestically, then the impact is minimal for you.
Okay, and then the last question. Does the 2012 version of NFPA 79 include functional safety requirements similar to EN ISO 13849-1?
Short answer, no. NFPA 79 2012 version does not have a normative or binding reference to EN ISO 13849-1, and in general, the standards in the U.S. have not adopted the performance levels or the safety integrated levels or the quantitative analysis that the standards 13849, 62061, etc. are embracing. If you follow where RIA 1506 revision is headed, I expect at some point in the next few years that the U.S. will embrace a light version, if I may, of the international or European standards that we're referring to. But NFPA 79 2012 in particular does not have that mandate in this version.
Okay, it looks like there's one more question that just came through the chat. This person is based in Europe, so give me 1 second. All right, the question is, I am European, so I know quite well the ISO 13949-1 and EN 62061. In your opinion, which are the main differences with the U.S. standards?
Main differences are, let me start with twofold. One is governmental or legal. In the U.S., standards, consensus standards, industry standards are developed by a consortium or collaboration of industry and are in effect voluntary. They are referred to by our government agencies and legal enforcement and judicial systems. When there is an accident or an investigation, our systems may refer to our U.S. domestic standards to look for state-of-the-art and common practice. So in Europe, effectively, I'm paraphrasing, the machine tool builder is responsible for machine safety, and compliance is mandatory and legally required. In the U.S., compliance with our standards are voluntary. The differences primarily between 13849-1, 62061, and the existing U.S. standards is the U.S. has effectively continued its observance of a EN 954-1 type of safety category and methodology. The U.S. has not embraced the safety integrity level or the performance level calculations and methodologies that those standards bring. We do not use those as of yet in the U.S.
Okay, let me check one. If there's anything else that's come in. No, I think we're good. So with that, we'll conclude this webinar session. Make sure to check out the rest of our upcoming webinars. Go to our website at usa.siemens.com/CNC4U. That's CNC, the number 4, YOU. Thanks to everyone for taking the time to join us this afternoon. Kevin, thank you so much for presenting on this informative topic, and we hope everyone has a great day. Thanks again.